Over to you.
Okay.
You are ready.
Hey, can you hear me?
Yes, yes.
Frankly, I just seen that this is already 3 hours in a row. I don't know how you can stay concentrated. So I'll try to make it light and easy. Um, but of course, feel free, if you need a little break, take a little break and come back. I will try to make it easy on you guys today, because today I'm really excited about this lecture. It's a lecture that I really, really like, and it's something that I found for myself where I got really deep understanding of the standard model is what I tried in this lecture today. So first, let me summarize what we did yesterday. And today I put the most up-to-date figure. And I think I told you this yesterday. It doesn't matter how long I look into this figure, I'm so excited. And that's what we did yesterday. What we did yesterday, we went through the construction of the CKM, discussed some properties of the CKM matrix. And the point that I like to make is that it works. You do all those measurements and it works. It's far from trivial, the fact that actually things are working. And this is the state of the art. What you see here are different measurements that I will not get into the details of those measurements, because I like to, in this lecture, I concentrate on the theory of the standard model theory. But this is all the measurement and this little thing that go much beyond this little whatever hands. It's where the things are made. And even if you zoom in, it's still roughly the same size as this little hand in this plane. So that's where I ended yesterday. I want to mention the following. The standard model is very special. A standard model is special already. A standard model is just a generic model that have the same gauge group and fields as the standard model, but without assigning any value for the parameter. It's already special. The flavor change neutral current only occurs through the W exchange. That's already far from a generic statement. And this standard model is even more special because that standard model, the CKM matrix, the one matrix that is responsible for flavor physics, is very close to the unit matrix, and it's far from a generic matrix. Okay? So that's kind of the takeout from yesterday. The standard model is far from special. It's very special. It's far from generic. And the fact that the data confirm the standard model is far from a trivial statement. It's really an amazing achievement of mankind. And I'm not overestimating it. It's really an amazing achievement of humanity. Okay, so that brings me to today's lecture. And today's lecture will be on flavor change in neutral current, or FCNCs. And let me discuss them. So before we discuss some acronyms, so FCNC stands from flavor change in neutral current, or currents in plural. I mean, that's one thing I don't know in English. And if someone who really know English well can tell me, if you have an acronym and you want to make it into a plural, do you add an S at the end or not? So when I talk about the plural of FCNC, should I write FCNCs with a small s at the end or not? I don't know the answer. I Google it and I got different answers. So I will not put the S in the end, and just from the context, if I talk about plural or singular. And FCCC is flavor changing charge current. And I want to give 2 examples. So mu go to 3 electrons is a flavor changing neutral current, because the exchange is neutral. Mu going to electron Nini bar, which is the standard muon decay, it's charge current interaction. B to C L Ni, which is the standard semi-leptonic B decay, is charge current, while B going to S L plus L minus is neutral current. Okay? And in this case, it's very easy to see. It's like you just see the change of the charge of the quark. If you have B to S, that's neutral. If you have B to C, that's charge, right? If you have B to U, it's charge. If you have B to D, it's neutral. Okay? The flavor change in neutral current, it's a very important concept in flavor physics. I would say that the whole story about flavor change in neutral current is what help us to actually understand the standard model. Okay? And understanding flavor changing neutral current is a very important thing of all these concepts of flavor physics. And before I get into the details of flavor changing neutral current, I want to discuss one important distinguish between diagonal coupling and universal coupling. So what is diagonal coupling? Diagonal coupling is that take any matrix and, think about some flavor space. You have the fields that live in the flavor space, right? And you have some matrix of coupling, and it's diagonal if we have only elements in the diagonal, like any diagonal matrix. The point is that diagonal coupling is a basis specific question. In general, when you have a matrix that has something only in the diagonal, when you move to a different basis, then it's not diagonal anymore, right? So being a diagonal coupling is a basis dependent statement. Okay? Now, what are universal coupling? Universal coupling are some coupling that are proportional to the unit matrix in flavor space. Okay? So think about a matrix that is like the unit matrix. It's 1, 1, 1. This matrix is diagonal in any basis, right? So the unit matrix, no matter how you rotate it, it's always a unit matrix, right? So for example, when we talk about the kinetic term is proportional to the unit matrix. So no matter what I do, it's the unit matrix. Okay, see, I have one question. Now I know how to chat, go to chat. Is mu2 electron standard model process? The answer is depend how you define the standard model. But in the standard model without neutrino masses, the way I define it, it is not. It's actually 0, okay? All I wanted to mention here is the fact that it's a neutral current interaction. And indeed, in the standard model, the prediction is that it's going to be 0, okay? And nobody, it has not been measured till today. It's a very strong bound on it. So coming back to the point I was making here, I hope you understand the difference between diagonal coupling and universal coupling. Of course, universal coupling is a subset of diagonal coupling. Universal coupling are also diagonal, but not diagonals are not always universal. Diagonal coupling is a basis dependent statement, and universal coupling is a basis independent statement. Probably I should have written it. Okay, so let me talk a little bit more detail in flavor change neutral current. And what we find in nature is that they are highly suppressed. And already yesterday, like exactly this time yesterday, I gave you some data from the PDG, and you guys already realized that just looking at the data, you see that flavor change in neutral current are generally suppressed. Historically, the first one that was measured and was very important in the history of physics was the comparison between K to mu nu and K long to mu mu, okay? This one is a charge current decay of the S quark, and this is a neutral current decay of the S quark. This one is S to U, and this one is S to D. And the branching ratio for this one is of order 64%. So almost 2/3 of the time a kaon decay this way, a K plus. And a K long to mu mu, the branching ratio is less than 10 to the minus 8. So it's a very, very rare process, okay? And historically, it was the fact that people didn't see this K. So historically, in the 60s, people knew only about 3 quarks. It was the up, down, and strange. And the fact that this one was not there made the prediction that there must be a 4th quark, which is now known to be the charm quark, that actually make these things very, very small, okay? So historically, the smallness of flavor change neutral current was already there to predict the existence of the charm quark. And now we've seen that flavor change neutral current are suppressed in charm and BDK. In particular, in charm, we see none. There's no flavor change neutral current that had been observed in charm decay, kind of a very strong statement. In B physics, we measure many of them, but all of them, all the B physics one that we measured are very small. The biggest one is B2S gamma, which is of order 10 to the minus 4. And there's many, many others. And just in the previous hours, some of them had been discussed, okay? So the statement that in nature, flavor change neutral current are highly suppressed is a data. So this statement is a statement based on the data, okay? Now we move to the theory and ask why, how can we see this phenomena that flavor change neutral current are suppressed in the theory? And the answer is twofold. The first one is that at tree level, there's no flavor change in neutral current. And this is really, really nice, okay? Just by saying, oh, something is very small, and I say, okay, no tree level, immediately you make it small because then it can only appear at one loop, and you already have suppression that go roughly like 1/16 pi squared, right? Great. And the coupling of all four bosons in the standard model, the gluon, the photon, the Z, and the H, they are all diagonal. And we're going to discuss them in great detail. We have to understand why they are diagonal. I already mentioned it yesterday, and today we'll get into the details, okay? And it's far from trivial why they are diagonal. We do have flavor changing at one loop, and the way to think about it is that charge current FCCC, flavor changing charge current square, give you neutral current. So if you change flavor by +1 and then change it by -1, you get 0 charge exchange, which is flavor changing neutral current. And the one loop gives you extra suppression in some cases. So what we're going to see is we understand why we have the suppression in the theory. The suppression in the theory comes from the fact that it's at one loop. And at one loop, we're going to see extra suppression factors in some cases. So that's what I'm going to discuss right now. Any question before I move on to the details? Okay, so let me move on. And what I like to do now, I like to explain why there's no flavor change in neutral current at tree level in the standard model. And let me start with the gluon and the photons. And the reason that they are diagonal is the same. And the reason is a symmetry argument. And the symmetry argument goes as following. What we have, the coupling of the gluon and the photon, because they are the gauge boson correspond to exact symmetry. They are not broken symmetries. Therefore, the kinetic term is moving into the diagonal, into the covariant derivative. And in the covariant derivative, we add the coupling to the gauge boson, okay? So it's always like this. The coupling to the gauge boson is the same as the derivative. And we always like to work in what we call the canonical basis. The canonical basis is the basis where the kinetic term is universal, right? And these are what we call particles. Particles are defined to have a canonical kinetic term, right? We normalize our particle to have a canonical kinetic term. So once we have a canonical kinetic term, all the unbroken gauge bosons must have the same coupling. And in particular, it's proportional to delta Ij. There's no flavor change in neutral current, okay? Symmetries are nice. We already know it. Symmetries are extremely important in physics, right? So it is the symmetry, it is the gauge symmetry that guarantee that the photon and the gluon, or in any model that you're going to construct that have a exact unbroken gauge symmetry, the gauge boson of the unbroken symmetry must be universal, okay? And that means that in any extension of the standard model, there must be a universal. And you know, sometimes you do a calculation and it appears as if you get tree-level photon, like the photon can couple to an S and a D in some BSM. That implies that you must have something wrong in your calculation, okay? If you are having this result, that means that something went wrong in the calculation. There's a symmetry that's guaranteed, okay? Any question on this? I hope we understand. Photon and gluon, yes, question, please.
Can you please elaborate on this point? Photon couplings are flavor diagonal.
Yes, so what I want to say is the following. The fact that the photon coupling comes from the kinetic term, okay? And I should have written it more explicit. The kinetic term for the photon is psi bar d slash psi, right? For any fermion is psi bar d slash psi, right? And the d slash is the one that have both the derivative and the coupling to the photon, right? That's the d slash, not the d slash, the d mu, right? And therefore, since the derivative must be diagonal, why the derivative must be diagonal? Because that's how we define particle. Coming back to lecture 1 in QFT, the way you define your particle is that the particle must have a canonical kinetic term, right? It must have the kinetic term of a particle must be psi bar d mu psi. Otherwise, it's not a canonical particle. Of course, you can work in any basis that you like, But that's the canonical basic. That's the basic where particles are propagating according to the Hamiltonian, etc., right? So once you actually define a particle and a particle has a canonical kinetic term, the coupling of the photon must be diagonal in this basis, because it is come from the symmetry. It's come from the gauge symmetry and the construction of the covariant derivative. Does it answer the question?
Yeah, thank you.
Good. Okay. Okay, good. So let us move on to the other neutral gauge boson and see why they don't have Flavour change in neutral current. In principle, the Higgs could have Flavour change in neutral current. The reason that the Higgs doesn't have Flavour change in neutral current in the standard model is because we have only one Higgs doublet. And when we have one Higgs doublet, we get this phenomena that the Higgs coupling is proportional to the mass. Why? Because phi, the Higgs field, after it requires a wave, is proportional to V plus H. V is a number and H is a field. So then we get the mass term, and the mass term is proportional to the Yukawa coupling times V. And the interaction of the Higgs is proportional to the same Yukawa coupling, right? It's the fact that we have only one phi tell us that the mass term and the interaction term are proportional to the same matrix, to Yij. So when I move to the mass matrix, when I diagonalize this, I automatically diagonalize this, okay? In order to appreciate it, let's see what happens when we have two doublets. When we have two doublets, we can have something like this. Oops, I have a typo here, sorry. We can have, say, something like y1 v1 plus y2 v2, because these are the these are the mass metrics that come from the two waves, wave of Higgs one of phi 1 and the wave of phi 2. However, what will be the interaction of phi 1? The interaction of phi 1 will be only proportional to y1, and the interaction of phi 2 will be only proportional to y2. Okay, so in this case, there's no proportionality, right? Because the mass term is proportional to the diagonalization of this sum of the two matrices y1 v1 plus y2 v2, where the interaction is proportional to just y1. And there's no reason that when I diagonalize this sum, I diagonalize y1, brr, such a hard thing to say, y1 and y2 separately. Okay? So the point is that many times people say, oh, why in the standard model there's only one Higgs? And when you look at the gauge sector, you say that's minimality. You don't really need two Higgses. One is enough, so why choose two? However, when you come to flavor physics, there's a big reason why we don't want two Higgses in the standard model. Because two Higgses give us flavor change in neutral current, while one Higgs guarantees that we don't have it, okay? For this specific reason, okay? Let me also mention that there are ways to avoid, we can still have two Higgs doublets and impose extra symmetries to avoid flavor change in neutral current. So there's some model building tricks, okay? So it's not if and only if. But the fact that we have only one Higgs doublet in the standard model, that's the reason that we don't have Higgs flavor change in neutral current, okay? Any question on this? Any question of the Higgs? Okay, so let's move on to the Z. And here the situation is as follows, okay? Let me first make the statement. If we have broken gauge symmetry and Z exchange is correspond to the broken parts of the SU2 cross U1, there's no FCNC when the following condition is met, okay? Let me say it and then I'm going to elaborate on it. All the field with the same quantum number in the unbroken symmetry also have the same quantum number in the broken symmetry. So let me explain, okay? In the standard model, we can have all the, say, for example, all the down-type quarks have electric charge Q equal minus a third. All of these quarks also have the same representation under SU2 cross U1. They all come from the 3, 1 minus a third under SU2, under the standard model, right? In principle, it doesn't have to be the case, right? Because Q, the electric charge, is equal to T3 plus Y. There's infinite way to get Q equal minus a third, Q equal minus a third from a combination of T3 plus Y, right? It doesn't have to be that all the charge minus third come from this kind of representation. Okay, I hope you get this following point. Okay, the fact that Q is equal to T3 plus Y tell us that there's infinite ways to get particles with the same Q, but they could have different T3 and different Ys. In the standard model, however, what we have is that all the particles that have the same charge, all the fermions with the same electric charge, have the same T3 and the same Y. Okay? It is this reason, the fact that all the particles with the same electric charge also have the same hypercharge and the same T3, tell us that the Z coupling is universal. Is actually, it's universal. In particular, it's diagonal. Okay? So let me show it in like a little bit of algebra. The coupling of the T3 part of the Z coupling, it's going something like this. It's Di, T3, and Dj. There's a lot of other factors, but I don't write them. They are irrelevant for flavor physics, okay? And this is what we write in general. Now, what happened? This T3 is diagonal because it's the T3 is for each of those, each of the Ds is the T3 of the Ds. However, what's happening is that we put the diagonalization matrix. You remember we talked yesterday about V left, V right, the one that we moved to the math basis. And that's what we have in the middle, okay? And what it is, what do we have? So if this T3 is universal, if all the particles that have the same electric charge have the same T3, then this T3 is proportional to the unit matrix. And then V dagger T3 V dagger is proportional to the unit matrix, and there's no flavor change in neutral current. However, if this T3 is not proportional to the unit matrix, then in general, V T3 V dagger is not proportional to the unit matrix, and in particular, it's not diagonal, and we have flavor change in neutral current. Okay? And today in the tutorial section that will come just after you have the break, then my graduate student, Mijo, he will go with you on a very detailed example where this is actually the case, where we do get flavor change in neutral current for Z exchange. And hopefully, once you're actually going to do one example where you do have flavor change in neutral current, you're going to appreciate the what's going on in the standard model and why we don't have flavor change in neutral currents in the standard model. Okay? So let me say that therefore, when we add things to the standard model, we can have flavor change in neutral current of the Z couple. For example, if we have a psi left, which is transformed like this, that is not a doublet, a left-handed fermion that is not a doublet, it will give us a flavor change in neutral current at 3 level from the Z coupling. And let me also mention one last thing, that if the same thing happen also when we have other gauge boson, like what we usually call Z prime, these Z primes also are going to have flavor change in neutral current if the coupling of the unbroken parts come from a different representation in the broken part. Okay, I know this point is a little complicated, but I really hope I was able to explain it. I mean, I don't see you. I look at the empty screen right now, but I really hope you understand it. And if not, ask me, and I'd be happy to elaborate on this point, because this is really such an important point about understanding why the standard model actually explains flavors so well, because the decoupling are universal, and that's because all the fermions with the same electric charge also have the same T3 and the same Y. Any questions? Okay, there's one. The chat. Is the fact that T3 is diagonal is accidental in the standard model? So I wouldn't say that accidental is the right word. I would say that it's by construction. People construct the standard model in this way in order to guarantee that we don't have flavor change in neutral current by the Z coupling, because we know that the data tell us that flavor change in neutral current is very, very small. So the standard model was constructed in a way to guarantee that the Z coupling is universal, and in particular diagonal. And the way to do it, the model building tool that we used in order to guarantee that the Z coupling is diagonal, is to make sure that all the quarks with the same electric charge also have the same representation under SU2 and under the U1 hypercharge. Any more questions? Yes. Okay, good. So let me summarize the story of three-level flavor change in neutral current in a standard model. In a generic model, we expect three-level FCMC. A generic model is not a standard model, just a generic. There's no reason that the flavor changing happen only with charge current. It could happen with neutral current. In the standard model, there's two ingredients that were used in constructing the standard model that guarantee that there's no three-level flavor change in neutral current in the standard model. First is that all fermions with the same charge, with the same electric charge, also have the same hypercharge. Okay? And second, that there is only one Higgs doublet. These two ingredients in the standard model guarantee that there's no flavor change in neutral current in the standard model. Okay? And therefore, we need to be very careful when we make extension of the standard model, because these two properties, these two constructions, can very easily just not satisfy in a generic model. Okay. So if we are okay with this, I want to move to flavor change in neutral current at one loop. And the point is the following. We understood why in general we have suppression of flavor change in neutral current, because there's no three-level exchange. And this suppression is roughly given by a loop factor. That means the amplitude is suppressed by 1/16 pi squared. Okay. Yet we do have flavor change in neutral current at one loop. And in this one loop, we actually get more suppression factors that are unique to the standard model. Okay. And there are two more suppression factors at one loop. One is CKM factors, and we talked about the fact that the CKM is far from generic, and therefore this suppression factor gives us because the CKM have small off-diagonal element that give us an extra suppression factor. And there's also mass factors, and that's also something we talked about, the fact that the masses in the standard model have a hierarchy. These mass factors give us an extra suppression factor, and that go under the name of GIM mechanism. Okay. So what I will get into the details soon, but what I want you to remember from this is the following. The loop factor, which is happening in any standard model, in a standard model, is universal. It's a one loop factor everywhere. The other factors, the CKM factor and the mass factors that are unique, they are coming from only from in this standard model, they are not universal. They actually give different value of suppression depending on the system. And therefore, we get some hierarchies of flavor change in neutral currents. As you remember, I just told you that we never seen it in charm decay, because the standard model suppression in the charm is very, very strong. Okay, and it's less in the physics. So we're going to see it in some detail. Okay, so let's look at the one loop diagram. This is B2S gamma, and I wrote this diagram. You know, there's actually more diagram, but I took one representative diagram, and I asked, what is this diagram? What is proportional to? So you look at the CKM factor, and I see, oh, what do I have here? Here I have VIB, VUB when you have an up, VCB when I have a charm, and VTB when I have a top. And what do I have here? Here I have VIS, right? So the amplitude, I have to add the three amplitudes, one from U, charm, and top. And therefore, the amplitude is proportional to VIB, VIS star, okay? Now I'm asking you, what is VIB, VIS star? That's a question. And, you know, if we were in front of each other, I would, you know, call out someone to tell me what the answer is. But now I hope someone can write it in the chat very quickly. What is this? What is the value of this, of VIB, VIS star, which is that's the factor that appears here?
0, 0.
0, yes, very nice. That's a general statement in teaching, right? Whenever you ask a question, what is the value of something? Half of the time, the answer is 0. Very good, okay? And this 0 is a real 0. It's 0 that comes from unitarity. And unitarity is a very, very big 0, right? It's something so fundamental. You cannot, it's not very, very small. It's a real 0, right? It's something you don't want to mess with it. Don't mess with unitarity, because unitarity, it's really just tells you that, time evolution is there, right? So if the fact that this is 0, then it looks as if this diagram vanishes, okay? However, this is not the case. And what we really have, we have the following thing. We have some mass dependence in this loop diagram, right? When you calculate loop diagram, you have some 1 over m squared, you have some propagators here, and the propagator carries some mass dependence, okay? So what we really have is the following combination. We have the combination of this CKM and some function of the mass, okay? So because of this CKM unitarity, we know that this M independent terms mass vanishes, right? And therefore, the total amplitude must depend on the mass. I hope this is clear. There must be a mass dependent on the amplitude. That's a very important statement. And the fact that I told you that in the indeed standard model, we have mass hierarchy, tell us that we're going to get some hierarchies coming into the game just because of this little story. Now, when I define this xi is mi squared over mw squared, when this one is small, which is the case for all the quarks but the top, then we have the following. Then the amplitude A is proportional to either x or x log x. It's depend on some details that I'm not going to get into, but it's always small. And the point is that it's, no matter what it is, it goes to 0 when x goes to 0, right? This is trivially goes to 0, and this one is still goes to 0. It's something that we, again, learned somewhere in our distant past, that x log x goes to 0 when x goes to 0, right? So the point is that we have a suppression, and this suppression goes to tell us that the amplitude actually must be proportional to the masses of the internal quarks, okay? Actually, it's going to, more precisely, it's proportional to the differences of mass. It's the mass dependence of the diagram. And this gives us the following thing. For a strange decay, it gives us a factor of mc squared over mw squared, which is numerically 10 to the minus 4. So you get a very strong suppression, extra suppression factor due to this, what we call the GIM mechanism. GIM mechanism is the story that what I'm telling you, okay? For charm, it's ms squared over mw squared, which is of order 10 to the minus 6. Okay, that's why in charm, we didn't see Flavour change neutral current yet. It's just huge, huge suppression, okay? And for BDK, it's not very important because for BDK, the thing that's going in the loop, the important part in the loop is the top, and the top is roughly of order MW, and then this number is order 1, and we don't get an extra suppression. So what we learned from this mechanism, from the G mechanism, is that because of the CKM unitarity, one loop diagrams are not generic. They must be proportional to the mass, and they come into the mass in a way that is small when the internal quark, the dominant internal quark, is light. Okay, and it gives us big suppression for kaons, huge suppression for charm decay, and it's not very important for BDK. Any questions on this?
Hello.
Yes, please.
You are deciding the dominant factor by considering the quark which is just lighter than that and has the highest mass, right? Like for S decades MC.
Oh no. Sorry. Actually, when you are saying it, I realize I misemphasized one point. Which quark is important in the loop? Okay, here all three quarks going in the loop. Which one is the one that is more important in the loop, right? I forgot to mention. The one that are important depend on the CKM factors, right? So when I have BDKs, the one that is important is the T, because B to T is the important. So when I have B to S, the two that are important are T and C.
Same family will be more important.
Yes, so the point is that actually you have to be careful and ask which one is the most important one. And the answer is not always very simple, but that's what enters. So what's really important, you have kind of a competition between the GIM mechanism that give you mass suppression and the CKM factor. So in kaon decay, if we have kaon decay, then the top one is very important because it's go like MT squared, but the CKM suppression factor is so strong that it kills you, okay? So actually, when you try to do it correctly, you have two suppression factors, CKM factors that happen here, and the mass factors. And you have to consider both, and then the answer is which one is more important. And for kaon physics, it turned out that the charm is usually more important, despite the fact that it's so light. And that's because the CKM factors of the top is so small. Okay,
so
thanks for,
we have to,
for the question. Yes, go ahead.
So we have to put in the numerical values. Unless we do that, we can't say anything.
Exactly, and that's exactly the point of the standard model. It's all what I'm telling you now. It's very unique to this standard model. That is it's really important for the numbers that we measure in our universe. It's not a generic property of any model. Okay, that's very important.
Okay.
And thank you for the question. And now when we talk, I know how I should have write those transparency. I should have really made this point, and it was implicit. So thank you for reminding me, and I hope now I made my point clearer. Okay, so I want to give a few remarks about the GIM mechanism. The first one is the fact that we have CKM unitarity and the three-level Z exchange are related. Okay, and the three-level Z exchange was something that I was just telling you, why we don't have it. However, if we add more quarks to the standard model, then the CKM become non-unitary, okay? Because you have something going in the loop. And then the situation is it's much more complicated. In particular, all those divergences are much more complicated. So the point I like to make here is that the GIM mechanism is, you have to be very careful when you add more quarks to the standard model. When you have a three-level Z exchange, then you also have to be very careful about what's happening at one loop, okay? When you do things at three level, it affects you one loop very dramatically. The second question I like to ask is the following question. What about the decoupling theorem? And let me say what is the decoupling theorem. The decoupling theorems make the following statement. When you take new particles and make them heavier and heavier, eventually you should not feel them. And this is very fundamental, if you like, to perturbation theory. It's go even beyond quantum field theory. Think about second order perturbation theory. You do sum over 1 over E of the states, and when the energy of the other states go to infinity, it's not affecting your theory. I hope it's very, very intuitive. When you have a particle that must go to infinity, it cannot affect your physics at the infrared, right? That's the decoupling theorem. It tells you that when you take a mass of a particle to infinity, it cannot affect your theory when you do the measurements, right? But here it looks like it's violated because actually the diagram is proportional to the mass. So when I take the mass heavier and heavier, then actually the amplitude is bigger and bigger, right? Rather than make it smaller and smaller, okay? I really want you to think about it, but unfortunately in this Zoom format, I would not be able to let you think about it too deeply, but let me just give you the answer, okay? By the way, before I give you the answer, let me tell you that these same phenomena also happen when you do electroweak precision measurement that I'm not going to talk about at all. But if you know about electroweak precision measurement and you know about the correction to what we call the T parameter or the rho parameter, you know that the correction to the T parameter to the leading order go like MP squared, go like the mass of the top squared. And again, it seems like violating the decoupling theorem. If I take the mass of the top to infinity, the rho parameter actually grows instead of going to be small as the decoupling theorem tells us, okay? So what is the answer for this apparent contradiction? The answer is that what's really important at the end of the day is the fact that you have a coupling. And what really played the role, I say it's the mass of the top, but the underlying physics that tells what the mass of the top is actually the coupling of the top, is the Yukawa coupling of the top. And then when I make the coupling higher, then of course I expect it to be more and more important, right? So the decoupling theorem actually tells us that I take the particle mass to infinity without affecting the coupling. However, if I at the same time make the coupling large, of course, I don't expect decoupling. Okay? Sorry, I hope this point is clear. Any question about this? Okay, so now I want to move to the story of meson mixing. And meson mixing, let me say a few words. It's an extremely important phenomena in particle physics. And we talk about things like kaon mixing or BB bar mixing. And there's two things that many times people mix. And this is what mixing is and what oscillation is. Mixing is the theoretical calculation from the fact that the mass eigenstate are not Flavour eigenstate. And the mass eigenstate are a mixture of things with a well-defined flavor. Okay? Is the fact that the kaon, k long, for example, is k plus k bar. Mean the mass eigenstate k long is a mixture of Flavour eigenstate k and k bar. Oscillation is the time evolution phenomena that when I start, say, from a kaon, this kaon can oscillate into a k bar. Or you probably also heard about neutrino oscillation. In neutrino oscillation is the phenomena that I start with a given flavor of neutrino, and I find it after some time that it becomes another flavor of neutrino. So this is the difference between mixing and oscillation. They are closely related because you measure mixing by oscillation, but they are not the same. So what I want to discuss now, I want to discuss actually somewhat of the formalism of the mixing, the formalism of oscillation, and why they are so important in understanding the standard model. So let me start with a two-level system, what is called Rabi oscillation in quantum mechanics, and I assume you've seen it before sometimes in your undergrad study. So let's take a quantum mechanics two-level system that I call 1 and 2, and they are the energy eigenstate. Okay? And then I can make some measurement, which I call flavor. You can call it whatever you like, it's quantum mechanics. And I said this operator that I call flavor, the eigenvalue of this operator is F1, which is 1 plus 2, and F2, which is 1 minus 2. It's really bad notation. I really don't understand why I use this bad notation. I should call it FA and FB. I don't want you to get confused with the 1 and 2. So what is, let's say that I start with a state that is a well-defined flavor. It's not a mass eigenstate, it's a superposition of 1 and 2. So this state, F1, I really hate my notation. It's killing me. Why did I do this? I mean, anyway, the time evolution of this state, F1, is then given by the following two exponents. It's 50%. There's some normalization factor that I don't write. It's e to the I delta ET over 2, 1, e to the minus delta ET over 2, 2, right? There's an overall factor here of e to the I E average T over, which is just an overall factor that I don't care. And then I ask, what is the probability to measure flavor F at some time T? It's given by this F1 over as a function of T times F1 all squared. I'm really sorry. I don't know how I messed up so much. Okay, this one is F1 of T. F1 of T projection over F1. So I take my state that I do time evolution and I project it into this state. That's what should have been here, okay? And what you find the following probability. The probability to measure F1 is 1 plus cosine delta E, and the probability to measure F2 is 1 minus cosine delta E. And that's the well-known phenomena of Rabi oscillation, okay? And what I really like to emphasize is the following. The oscillation frequency is delta E. What sets the oscillation frequency when I have a two-level system is the energy difference between them, okay? And what is the relevant parameter is delta ET, okay? If T is very, very small, there's no time for oscillation, right? If T is very, very large, I have many, many, many oscillation when I practically average over them, okay? And this parameter that I define as X is delta ET is what set the oscillation in the quantum mechanics system. Any question on the quantum mechanics system? How we have a two-level quantum mechanics system that have oscillation? Okay, so now what's happened when we have mesons? It's basically we just take quantum mechanics to make the relativity. What E become M? Why it become M? Because I'm talking about being basically in the rest frame. And my flavor eigenstates are basically my K and K bar, and my mass eigenstates say are K short and K long. And how do I do a measurement? How do I measure the flavor? I measure the flavor by the decay. Okay, so if I have a kaon that decay to a lepton, I know it's a kaon. If it decays into an anti-lepton, I know it's an anti-kaon, right? So what I'm really doing, I just produce a kaon, I let it evolve in time, and then it's decay. The decay is a quantum measurement. That's very important. Okay? In quantum mechanics, say, oh, I measure things, and it's up to me to say when I measure them, right? Here, when I have a particle it's the decay itself that do the measurement for me. When the particle decay, it's the tagging, it's made a tagging, and it's a quantum measurement, okay? Particle decay, it's a quantum measurement, okay? So we get the same result. The probability, if I start with a kaon, the probability to stay a kaon is go something like this, and the probability to be an anti-kaon go like 1 minus cosine delta mt. So now what set the frequency of the oscillation? It's delta m. Instead of delta E in the quantum mechanics case, in particle phase is delta m. It's the mass difference between the two mesons. And what set the scale? It's delta mt, but T is roughly 1 over gamma. The typical time scale is 1 over the width, okay? So the typical time scale that I care about is delta m over gamma, okay? When delta m over gamma is very small, there's no time for oscillation. I measure it very early. When X is very, very large, I average over the oscillation. Any question on this? No? Okay, so now I want to talk about how to calculate delta M. There's 4 mesons that we have in nature that we care about. They are the K, the B sub S, and the D. And I'm asking you several questions here. I'm not going to actually elaborate them because I see the time is running late, because I start kind of late, I guess, but I will skip those. But I want you to think about them later on when you are, when you have some free time. They're going to actually help you understand why we only have 4 mesons that we care about in nature. But let's consider those 4 mesons. And let's, for example, take a B. And the B and the B meson mix via the weak interaction. Why? Because I can have an amplitude that take B into a B bar. That's a flavor change in neutral current process, right? I take a B and it becomes a B bar. There's no charge exchange. The B D bar become a B bar D. And in the loop, what we have, in the standard model, it's a loop. Beyond the standard model, it could happen at tree level, of course. And then we have the following mass metrics, okay? The thing in the diagonal is the fundamental mass of the B meson. And the off-diagonal term are these weak interaction terms that actually move me from a B to a B bar. This mass matrix, it's a B bar mass matrix. It's a B bar, B bar here. You look at this mass matrix, you know how to diagonalize it. The eigenvalue are MB plus minus M weak, and delta M is M weak, okay? Delta M is the difference, and M is the sum. Just, how you do it, you say the trace is 2MB, and the determinant is MB squared minus M weak squared, okay? And then you say, oh, the sum of MH plus ML is 2MB, that's the trace, and the product, which is the determinant, is MB squared minus M weak squared, which is this. So that's how you know that this is the solution these are the eigenvalues of this system. Good. So we understand what is delta M. Delta M is basically the off-diagonal term in the mass basis, which is basically the amplitude of B going to a B bar. Okay? And the reason that we care about it so much, because it's at FCNC. So we can learn something about the underlying system and the underlying theory, because flavor change intercurrent are so important because they are not there at tree level. So how we do this calculation in the standard model, it's given by the box diagram, and you just write it and you calculate, and you find that it has 4 different CKM combinations, okay? And 2 different uptype quarks run here. So it's like we did before in the one loop diagram for B2S gamma, but here it's a little more complicated because it's kind of twice the CKM factors, and the function f actually depend on 2 masses. But it's a very similar story. The mass it must depend on the mass because the mass independent terms vanish due to unitarity. And we find that the leading order, this F goes like the mass squared of the heavier M in the loop, okay? So again, I'm not going to the details. All I'm saying is that it's a flavor change neutral current, and therefore it depends on the masses running in the loop. And in the limit of small masses, that is when Mi is much smaller than Mw, then we get a large suppression of this process, and we can learn something about the underlying theory. And we just have different suppression, just like we talked about when we talked about the GIM mechanism. For Keon physics, the suppression is MC squared because the charm is the important one running in the loop due to the CKM factor. For D-mixing is MS squared. That's why D-mixing is so suppressed. And for B and B sub S, there's no suppression because the top is of order the mass W, okay? And therefore, mixing phenomena that we can do by using oscillation can tell us things about meson mixing. For example, using B meson, we get VTD, okay? And I'm not going to get into the subtleties of QCD, etc. You're going to have some lecture just about it. So let me tell you one last thing about meson mixing, that in general, there's another parameter in meson mixing, which is not only the oscillation, it's also the delta gamma over gamma, which we call Y. This is the width difference between them. In general, the two mass eigenstate doesn't have to have the same width. And we call it Y, which is delta gamma over gamma. And we see that actually the four mesons that we have in nature all have different values of X and Y. So for Keon, X is order 1 and Y is order 1. Surprisingly, both of them are almost exactly 1 to a very good approximation. That's an accidental thing. The D meson, only very recently we measure both X and Y. Both of them of order 10 to the minus 2. X is half 10 to the minus 2 and Y is 0.7 10 to the minus 2. The B sub D meson, X is of order 1, it's 0.7 roughly, and Y is of order 10 to the minus 2 theoretically. We did not measure Y in the B sub D system. And in the B sub S, X is of order 10, it's more like 20, and Y is of order 10 to the minus 1, it's something like 0.08. So what we see that we have 4 mesons in nature, and surprisingly enough, all of the X and Y are roughly order 1s, are not 10 to the minus 7 and not 10 to the plus 7. And each of them has different values of them. So therefore, the approximation that we are making when we deal with each of those 4 is different. I'm not going to get into the details, but again, it's something very special to the standard model. It's not a generic thing about any standard model. It's the value of the CKM and the value of the masses of the quarks that tell us where we are, okay? How to measure mixing. I'm not going to get into the details because basically you just had it in the lecture before and I'm running out of time, but I just want to actually make the point that I already made, that mixing measurements is done by oscillation. By using flavor oscillation, we actually extract the mixing parameter, just that you know how it is. So let me conclude this lecture by saying that meson mixing is a very important process because it's flavor change in neutral current. And we have loop suppression, it's a loop, CKM suppression, and GIM suppression. Okay? And what I like to ask you, I know it's really late, but I still hope that someone can answer this so I see that my point came along. The first question is, what do we get in each meson? Do we get loop suppression? Where do we get CKM suppression? Where we get GIM suppression? Okay? And for each of them, tell me, is it from a standard model or from this standard model? Which of this suppression is there? So you have 4 mesons. These are the 4 mesons, K, D, B, D, and B sub S. And I want you for each meson to answer the following question. Do we have loop suppression? Do we have CKM suppression? Do we have GIM suppression? And then to answer, is this in any standard model or in this standard model? So I'm going to leave it here with an open question for you, and I hope you will have some time to do it. And that's it for me for this lecture. And as I said, in about an hour, Mijo, my student, he will join you guys and he will run an exercise that has to do with the 3-level Z exchange, flavor change, unit alkaline Z exchange. Okay, that is for now.
Thank you, Yuval. Any questions? Any quick questions before we break for lunch? I think everybody is tired.
I know I mean, I'm so sad. I'm in like my 3 hours in a row, and then you get into this deep stuff. Anyway, I still hope you guys got kind of the main points. And if you think about question, you can ask me during the tutorial question, or you can ask me when we meet again this afternoon.
Hello, sir.
Yes, please go ahead.
Yeah.
Yeah. So, is there any other observable than X and Y in mixing, which can
Yes.
tell us?
Yes. So the X and Y are the important ones that are there when we talk about CP conserving systems. And what I'm going to do this afternoon, I'm going to talk about CP violating system. And in CP violating system, there's actually many more observables that are related to the mixing, and they have actually an interplay between mixing and decays. I'm going to spend a lot of time on this this afternoon in the second lecture. And X and Y are the ones that are important for CP conserving one. And there's more, and I will discuss them. Thanks.
There's one question, Yuval, in the chat box.
Okay, let
Can
me
you,
see.
yeah, if you are able to
Yeah.
see the chat box.
Oh, can you please discuss a little more about long distance effects? Okay, so I didn't actually discuss this in any great detail. So the calculation that I was just mentioning kind of very briefly, I said, okay, here is the thing, here how you kind of make the calculation. Clearly, I don't have the time to go into the details. Now, one very important point here is as following. We make an assumption that the quark level calculation is relevant for the what we see for the mesons. And this moving from quarks to meson is a huge, huge deal, okay? Why when we do calculation with quarks, we can actually treat and apply it for mesons? And the answer is that in sometimes we understand why it is. For example, in some heavy quark limit, we understand how to do it. But in some other case, this assumption is actually not very good. And again, without getting into the details, I can actually get a full lecture just about this. Let me say that for kaon physics and B physics, we believe that doing the calculation in terms of quarks, it's okay, because the charm is heavier than the kaon, and the top is heavier than the B. And when something is much heavier than what you have, it must be far off shell. And when it's off shell, you don't care about some strong interaction of QCD. In charm physics, however, this is not the case, because in charm physics, the intermediate quarks, the dominant intermediate quark is the strange quark. And the strange quark can go on shell. And when it's go on shell, that's what we call long distance effect. It's long distance in the sense when then something is on shell, it can really propagate in real space. And therefore we call it long distance. Short distance means everything is off shell. Long distance means things can actually go on shell. And when things can go on shell, you don't trust your quark level calculation because there's a lot of QCD effects. And in charm physics, the effect is actually an enhancement of a factor of roughly 100 compared to the quark level calculation. So in charm physics, when you calculate charm mixing, the calculation in terms of quarks is underestimating the effect by a factor of 100, which is a huge deal. Okay, so I could talk much more about it, but let me just stop here because we don't, I don't want to get too much. But like I said yesterday, we, in our book that I keep advertising, in section 10 and 13, we actually have much more details. And in the TASI lecture that I gave you, there's actually, again, much more details that I hope they are explained in a way, and I encourage you to go and read it.
Okay, if there are no more questions for the time being, we thank Professor Grossman and we'll be